In the late 19th and the early 20th century, physics was at its peak. Several physicists were beginning to realize that there were a lot of things that were logically inconsistent with classical theories of physics. One of the mysteries was surrounding the theory of blackbody radiation. In this series, we will talk about the blackbody radiation and how it gave birth to quantum mechanics without skipping the mathematics. Today's episode includes the preliminary ideas of thermal radiation and the derivation of Kirchhoff's law. So, without any further delay, let's get started. When radiation falls on matter, there are three kinds of process that can take place. It may partly be reflected, partly absorbed, and partly transmitted. If small r is the reflectance, small a the absorptance, and small t the transmittance, then plainly we can write r plus a plus t equal to 1. The values of small r, small a, and small t may be different for different wavelengths. We thus use to denote r lambda as the reflectance or the reflecting power of a substance for the wavelength lambda, and similarly a lambda and t lambda for the other two. For bodies having a lambda equal to 0 and t lambda equal to 0, it follows from the equation that r lambda equal to 1. Such bodies are called perfectly white bodies to which a piece of chalk approximates in so far as visible radiations are concerned. However, r equal to 0 and t equal to 0 gives the absorption coefficient a equal to 1. Such bodies are called perfectly black bodies, the nearest approach to which is lamp black. A perfectly black body can neither reflect nor transmit light that falls on it. It thus appears black. Perfectly black body is also obviously an ideal conception. Such a body, when heated to high temperatures, emits radiations of all wavelengths, and such radiations are called total radiation or black body radiation. The example of a black body is Fairy's black body, which is a cavity with a small hole on it. It consists of a double walled metallic shell, inside being lamp black and the outside nickel polished. It has a small opening opposite to which there is a small conical projection on the inner wall. The lamp black hastens to attain the constancy of temperature, and the outer polish makes the enclosure impervious to heat. The projection prevents any direct reflection of rays back through the opening. When any radiation enters the enclosure, it suffers multiple reflections inside and is eventually absorbed so that practically no radiation comes out through the opening again. Interestingly, the black radiation and an ideal gas possess some fundamental points of similarity, and that is why the ordinary thermodynamic relations may as well be applied to this temperature radiation. An ideal gas, as pictured in kinetic model, is an assembly of particles in having all possible velocities and moving in all directions. The black radiations from a constant temperature enclosure similarly have all possible wavelengths and proceed in all directions. The molecules of an ideal gas exert a pressure on the walls of the container, and so does the black radiation on a surface placed normally to it. The internal energy of an ideal gas is very similar to the energy density of the black radiation. Ideas regarding radiant energy were much confused during the 18th century. In 1792, Pierre Prevost clarified the nature of radiation through his exchange theory of heat. It stated that substances at all temperatures radiate energy, and it increases with the increase in temperature, and it also is not affected by the presence of surrounding bodies. It gave an insight about what thermal radiation might be, but that was as far as it could go. The real journey started with Gustav Kirchhoff. In 1859, he posed the problem of measuring and explaining temperature radiation. At that time, it was known that heated solids like tungsten and gases emit radiation. To find the true nature of thermal radiation, Kirchhoff imagined a cavity whose walls are heated up so that they emit radiation which is trapped inside the container. The walls of the container can emit and absorb radiation. Now, let us define two very important quantities that enter into Kirchhoff's law. One Emissive power. The emissive power E lambda of a body for radiation of wavelength between lambda and lambda plus d lambda is the amount of radiation emitted per unit area of the body per second, normally in unit solid angle in the axial direction of the solid angle. The emissive power of a body is a function of lambda and has a spectral character. The total emissivity or total emissive power E is given by this equation. Now the second is absorptive power. If dq lambda be the amount of radiant energy falling on a body in the form of radiation in the wavelength range lambda and lambda plus d lambda, a fraction of that is absorbed by the body. If a fraction a lambda dq lambda of 8 is absorbed by the body, then a lambda is called the absorptive power of the body for the wavelength lambda to lambda plus d lambda. Now let us have a look at Kirchhoff's law. It states that the ratio of emissivity and the absorption coefficient of an object for a wavelength is same for all bodies at same temperature and is equal to the emissivity of a black body at the same temperature. Symbolically, it can be written as E lambda by A lambda equal to capital E lambda, where capital E lambda is the emissive power of a black body. This equation is the mathematical form of Kirchhoff's law, and it states that the ratio E lambda by A lambda is a universal function of lambda and temperature T. From this equation, we immediately find that if we fix lambda and capital T, the ratio E lambda by A lambda is fixed, implying that E lambda is directly proportional to A lambda. In other words, good absorbers are good emitters and good reflectors are bad emitters. In order to derive the law, let us assume an enclosure at a uniform temperature T with walls opaque to radiations of all wavelengths and thermally insulated from the surroundings. The enclosure is filled with temperature radiation emitted by the walls. A body of emissive power E lambda and absorptive power A lambda is placed inside the enclosure at a large distance from the walls. Now whatever be the temperature of the body, it finally attains the temperature T of the enclosure. In the equilibrium state, the entropy becomes maximum only when the temperature differences vanish. Since it acquires finally the temperature T of the enclosure, the total energy absorbed by it will be equal to the total energy it emits in the equilibrium state. Thus, the total energy absorbed by the body is independent of its position and orientation with respect to the walls. As the different surfaces of the body have different absorption coefficients, this is possible only when the radiation inside is isotropic. Now, the amount of energy emitted by an elemental area dA of the body in the direction between theta and theta plus d theta and phi and phi plus d phi is given by this expression. The theta and phi are the angles in spherical polar coordinate system. Here, E lambda d lambda dA cos theta is the energy radiated per unit solid angle and sin theta d theta d phi represents the solid angle. The total amount of energy emitted by dA in all direction and for all possible lambda is given by this integral. The limits on the angular part are such that theta varies from 0 to pi by 2 and phi varies from 0 to 2 pi because the element can only radiate in the outward direction. So this expression gives the energy emitted by a small area element in all direction and in all wavelengths. Now to find the emission for the whole body, we have to simply integrate over the area element. To derive the absorption, we need to find the amount of energy emitted by an elemental area dA prime of the enclosure in the direction dA of the body. Let E lambda be the emissive power of the enclosure walls. The area element dA of the object is at a distance smaller from the area element dA prime of the enclosure wall. The solid angle subtended by the area dA at dA prime is given by dA cos theta by r square, where theta is the angle between the direction of dA prime with the direction of emission. So the energy emitted by dA prime in the direction of dA is given by dq lambda Now, if A lambda is the absorptive coefficient, then it will absorb A lambda multiplied by dq lambda amount of energy. So the amount of energy absorbed by dA of the body is given by this equation. In order to simplify the calculation, we rearrange this equation and we notice that dA prime cos theta prime by r square is the solid angle subtended by dA prime at dA, which again can be replaced by sin theta d theta d phi with the same limits as the previous one. Now integrating this, we have the total energy absorbed by dA from the total surface of the enclosure for all wavelengths. So for the whole body, therefore, the absorption is given by this integral. Now here comes the important condition. In the equilibrium state, the temperature of the body is fixed, which is same as the enclosure walls. This means the amount of energy radiated per unit time of the object is equal to the amount of energy absorbed per unit time. This yields that the two integrals are the same. From this relation, we must obtain that the integrands are equal. If the same object is placed in another enclosure of different shape and nature, but at the same temperature T, we have the relation where E prime lambda is the emissive power of the enclosure. Now, as A lambda and E lambda only depend on the object and not on the surroundings, we must have E lambda equal to E prime lambda. If a black body is placed inside the enclosure, we have A lambda equal to 1 and capital E lambda is equal to small e lambda. This means the radiation in any hollow enclosure is independent of the nature and shape of the walls and is identical with blackbody radiation at the same temperature. With this, Kirchhoff's law now immediately follows, which says at any temperature the ratio of the emissive to the absorptive power of a substance is a constant and is equal to the emissive power of a perfect black body. This law is valid for temperature radiation only and does not hold for radiations obtained by chemical action or by electric discharge in gases. Prior to Kirchhoff's studies, Balfour-Stewart first showed for a particular wavelength the ratio was the same for all bodies. But it was Kirchhoff who explicitly considered that the universal value of the ratio as a function of wavelength and temperature. The importance of Kirchhoff's law can hardly be overestimated. In a sense, it opened up two entirely new branches in physics. One is astrophysics and the other is spectroscopy. Newton demonstrated that sunlight consists of a spectrum of 7 colors. Fraunhofer, in repeating Newton's experiment, found that the solar spectrum is not continuous, but is crossed by a large number of dark lines, and he designated the prominent ones by the letters A, B, C, D, etc. These are the so-called Fraunhofer lines, but neither Fraunhofer nor his contemporaries could understand how the Fraunhofer lines originate. Similar cases were found for other stellar spectrums also. The explanation given by Kirchhoff completely solved this problem. He supposed that the central core of the Sun is a glowing mass that emits a continuous spectrum without the dark lines. But this light has to pass through a relatively cooler mantle surrounding the core. The mantle, however, is hot enough to have all the elements like sodium, copper, etc. in the gaseous form. Sodium emits D lines when excited, so when light falls on it, it will absorb the same light and let others pass through. Thus, the gases in the outer mantle deprive the continuous spectrum of those particular lines which they themselves can emit and give rise to the black lines. Kirchhoff's discovery is of still far-reaching consequence. It asserts that every different types of atom, when properly excited, emits light of a different wavelength characteristic of the atom. So each atom can be identified by the particular line it emits. From this came the important and significant branch known as spectroscopy that aims at identifying elements by their characteristic lines. Although having this much importance, Kirchhoff's law cannot determine the universal function capital E lambda which only depends on the wavelength and temperature. It was impossible to derive that using the knowledge of thermodynamics available at that time. But in the later years, Wien first gave an expression for the universal function. We will explore that in the next video, so stay tuned for that. Thank you for watching. I hope you liked it. Please like and share this video, and to see such videos in future, do subscribe.